Hello everyone, hope all of you are fine. Today we will learn about block data transfer, DMA, parallel interface, serial interface, SCSI, and the types of serial interface. First, block data transfer. A block is a sequence of bytes or bits, usually containing some whole number of records, having a maximum length, that is a block size. Data thus structured are said to be blocked. The process of putting data into blocks is called blocking, while deblocking is the process of extracting data from blocks. Blocked data is normally stored in a data buffer and read or write on a whole block at a time. For some devices, such as magnetic tape and CKD disk drives, blocking reduces the amount of external storage required for the data. Direct memory access, in short, it is called DMA. DMA is a feature of computer systems that allows certain hardware subsystems to access main system memory, independent of the central processing unit or processor. Without DMA, when the CPU is using programmed input-output, it is typically fully occupied for the entire duration of the read or write operation and is thus unavailable to perform other work. With DMA, the CPU first initiates the transfer and then it does the operations while the transfer is in progress, and it finally receives an interrupt from the DMA controller, that is called DMSC, when the operation is done. This feature is useful at any time that the CPU cannot keep up with the rate of data transfer, or when the CPU needs to perform work while waiting for a relatively slow input-output data transfer. DMA is also used for intra-chip data transfer in multi-core processors. DMA sends read control signal to peripheral device and puts the destination address and read signal on address and control buses for memory. As is by transferred, the destination address is incremented by 1. The DMA transfer is initiated by input-output devices and the DMA controller takes over the processor's access cycles and performs memory operations. A DMA controller or its active channel can be in one of 6 working modes, such as ideal mode, single transmission mode, block transmission mode, transmission on demand mode, cascade mode, or verify mode. Small Computers System Interface, in short SCSI, is a set of standards for physically connecting and transferring data between computers and peripheral devices. The SCSI standards define commands, protocols, electrical, optical, and logical interfaces. SCSI is the most commonly used for hard disk drives and tape drives, but it can connect a wide range of other devices, including the scanners and CD drives, although not all controllers can handle all devices. The SCSI standard defines command sets for specific peripheral device types. The presence of unknown as one of these types means that the theory it can be used as an interface to almost any device, but the standard is highly pragmatic and addressed toward commercial requirements. Generally, the SCSI bus can overlap various data transfer requests by the devices. Besides, in SCSI transfers, the processor is not aware of the data being transferred. So, how are the SCSI devices connected to a personal computer system? Internal devices connect to a SCSI controller with a ribbon cable. External SCSI devices attach to the controller in a daisy chain using a thick round cable. In a daisy chain, each device connects to the next one in the line. SCSI devices come in two basic types, that are single-ended devices and differential devices. Single-ended devices use one data lead and one ground lead to establish single-ended signal transmission over the bus. And in differential devices, it uses two data leads, neither of which are at ground potential. A parallel interface refers to a multi-line channel, with each line capable of transmitting several bits of data simultaneously with facilities of parallel communication. In data transmission, parallel communication is a method of conveying multiple binary digits or bits simultaneously. It contrasts with serial communication, which conveys only a single bit at a time. This distinction is one way of characterizing a communication link. Examples of parallel mode communication include connection between a computer and a printer. Parallel interfaces are usually associated with printer connections, but several technologies implement parallel interfaces, including HIPPI, SCSI, OFDM, PCI bus, etc. HIPPI is High Performance Parallel Interface. It is a high performance parallel interface that is used in data centers and supercomputer applications. Small Computer System Interface, in short SCSI, is a parallel interface for disk storage devices that is characterized by 50-pin or 68-pin connectors. OFDM, that is orthogonal frequency division multiplexing, is a multi-carrier modulation scheme in which many parallel data streams are transmitted at the same time over a channel which is transmitting only a small part of the total data rate. And lastly, PCI bus. The PCI bus is the peripheral interface bus inside most desktop computers and servers. Most systems implement the 32-bit PCI bus, but 64-bit PCI bus systems should be selected when high input-output speeds are required. Today, parallel ports follow the IEEE 1284 standards defined in the early 1990s. It specifies the traditional 25-pin D connector and Synchronous connector as well as a new 36 conductor connector that is smaller than the Synchronous connector. The connector has better electrical and physical properties. The parallel interface has been expanded with enhanced parallel port and extended capabilities port, while retaining backward compatibility with the original SPP. EPP, that is Enhanced Parallel Port, has a bidirection mode that allows both devices to communicate. Intelligent printers, for example, use this mode to report status information back to the computer. EPP is also 10 times faster than original Synchronous interface. On the other hand, ECP, that is Extended Capabilities Port, has all the features of EPP and also provides data comparison via run length encoding, that is RLE. repetitive scanner and printer data benefits from the compression. Under Windows, PCP uses DMA channels and buffers to move data. The personal computer serial interface is one of the oldest established connection points for personal computer peripherals. A serial interface is a communication interface between two digital systems that transmits data as a series of voltage pulse down a wire. Essentially, the serial interface encodes the bits of a binary number by their temporal location on a wire rather than their spatial location within a set of wires. A serial port can only transmit one bit of data at a time, whereas a parallel port can transmit many bits at once. The serial port is typically the slowest port you will find on your PC, if you find one at all. The most new computers have replaced serial ports with much faster and more compatible USB ports. We distinguish two types of serial transmission depending on the clock and data synchronization, that is, synchronous transmission and asynchronous transmission. In both transmission types, serially data sent are formatted in frames with fixed structures and lengths. In synchronous transmission, data moves in a completely paired approach in the form of chunks or frames or blocks. Synchronization between the source and target is required so that the source knows where the new byte begins, since there are no spaces included between the data. Synchronous transmission is effective, defendable, and often utilized for transmitting a large amount of data. It offers real-time communication between linked devices. Before data is transmitted, it is first separated into blocks of sentences. The blocks are then transferred over the communication link to the target location. There are no beginning and end bytes. The data transfer rate is quicker, but there's an increased possibility of errors occurring. Over time, the clocks would get out of the sync and the target device would have the incorrect time. So some bytes could become damaged on account of lost bit. To resolve this issue, it's necessary to regularly resynchronize the clocks, as well as to make use of check digits to ensure that the bytes are correctly received and translated. The characteristics of synchronous transmission is there are no space in between characters being sent. Timing is provided by modems or other devices at the end of the transmission. Special sync characters goes before the data being sent. The sync characters are included between the chunks or blocks of data for timing function. In asynchronous transmission, data is sent in form of byte or character. The transmission is the half duplex type transmission. In this transmission, start bits and stop bits are added with data. It does not require any synchronization. There may be gaps or spaces in between characters. Synchronous protocols are generally flexible, since all the devices need to exchange information can do so at their own natural rate. Be this fast or either fast or slow. A clock signal is no longer necessary. Instead, the devices behave asynchronously, wait for the handshaking signal to change state, indicating that some transaction is about to commence. The handshaking signals are generated by the devices themselves and can occur as needed and do not require any outside supervisory controller such as clock circuit that indicates the occurrence of data transfer. The RS-232C protocol uses an asynchronous scheme that permits flexible communication between computers and devices using bite-sized data blocks, is framed with start, stop, and optional parity bits on the data line. A more advanced communication protocol is the Asynchronous Transfer Mode, in short ATM, which is an open international standard for the transmission of voice, video, and data signals. The versatility of this mode allows it to simulate and integrate well with legacy technologies, as well as offering the ability to guarantee certain service levels, generally referring to as quality of service parameters. Now there is a comparison between the synchronous and asynchronous transmission process. In synchronous transmission, data is transmitted in the form of blocks, while in asynchronous transmission, data is transmitted one byte at a time. Synchronous transmission needs a clock signal between the source and the target to let the target know of the new byte. In comparison with asynchronous transmission, a clock signal is not needed because of the parity bits that are attached to the data being transferred, which serves as a start indicator of the new byte. The data transfer rate of synchronous transmission is faster since it transmits in blocks of data compared to the asynchronous transmission, which transmit one byte at a time. Asynchronous transmission is straightforward and cost-effective, while synchronous transmission is complicated and relatively pricey. Synchronous transmission is systematic and necessitate lower overhead figures compared to the asynchronous transmission. Both synchronous and asynchronous transmission have their benefits and limitations. Asynchronous transmission is used for sending a small amount of data, while synchronous transmission is used for sending bulk amounts of data. Thus, we can say that both synchronous and asynchronous transmission are essential for the overall process of data communication. That's all for today. Stay well. Thank you.